everyone, my name is Imanakia.
Hi, my name is Wong Yong Ki.
My name is Muhammad Faris binti Idris.
Hi, my name is Aiman Fikri bin Musiful.
Hi, my name is Hari Darshan Rao.
And we are from Group 10. Our project focuses on failure modes and effect analysis, or known as FMEA, for the energy storage system in electrical vehicles. As EV adoption increases, ensuring the safety and reliability of their energy storage is critical. Our study aims to identify failure risks, analyze their effects, and propose solutions to improve system reliability. Despite technological advancement, ESS failures remains a major challenge. Issues like overheating, electrical faults, and software malfunctions can lead to serious safety hazards and financial losses. Without proactive failure analysis, these risks may go undetected until critical failures occur, making FMEA essential for improving ESS reliability. Our project focuses on three main objectives: identifying potential failure modes in the ESS of EVs, analyzing their causes and effects on system reliability and safety, proposing effective safeguards and mitigation strategy based on our FMEA findings.
Assalamualaikum. Today I'll be discussing FMEA on EV energy storage system, the key process that ensures safety and reliability in electric vehicles. FMEA, or failure modes and effect analysis, is a structured method to identify potential failure modes, analyze their effects, and develop strategies to reduce their impact. The ultimate goal is to make EV system more reliable by taking preventive steps early. So this flowchart show the FMEA process. The first one to identify system component, the next one to identify potential failures, the third one to understand the consequences of each failure, next to pinpoint the root causes, the fifth one to prioritize risks based on severity and likelihood, next one to develop preventive measures. So last one is to continuously refine strategy for better reliability. So this is a common energy storage options in EV. Lithium-ion battery pack, supercapacitor, advanced battery technologies. So this system store electricity and distribute it to the engine, computer, and other EV parts as needed. So the key components of EV energy storage system: battery pack contains module of cells for energy storage, BMS to track battery health, thermal management system to ensure battery operate at a safe temperature, electrical connection protection device to manage electrical flow and prevent overcurrent. So there are some common failure modes in EV, which is overcharging, overheating, vibration damage, terminal corrosion, and BMS malfunction. So why FMEA is important is because enhance dependability, safety, and performance, identify and mitigate risks, and improves overall product quality and safety.
Moving on to system boundary and failure incidents related to energy storage system. Failure in energy storage system occur due to a combination of thermal, mechanical, and electrical stress. Excessive heat, physical damage, and electrical fault can compromise battery integrity, leading to hazardous failure. Additionally, material limitations such as the lower thermostability of nickel-rich chemistry increase battery vulnerability. Manufacturing defect, including poor assembly and contamination, further contribute to failure risks. One of the most critical failure mechanisms in energy storage system is thermal runaway, where excessive heat triggers uncontrollable chemical reaction within the battery. This can escalate to thermal propagation, where heat spreads to nearby cells, leading to a larger scale failures. Electrochemical reactions such as lithium platinum and electrolyte decomposition further degrade battery performance. If vent gases are not managed properly, toxic emissions can cause safety and environmental hazards. Energy storage system failure can cause fires, explosion, and system malfunction, posing risks to both users and infrastructure. For electric vehicles, energy system storage failure may result in sudden power loss, affecting performance and user safety. Additionally, hazardous material leak can contaminate air, soil, and water, leading to long-term environmental damage. On top of that, failure leads to higher maintenance costs and reduced system reliability. To prevent energy system storage failure, multiple safety measures must be implemented. Battery management systems, BMS, play a crucial role in monitoring temperature, voltage, and current to detect early signs of failure. Efficient cooling and ventilation systems help regulate temperature and prevent thermal runaway. Smart protective mechanisms such as circuit breakers and automatic shutdown features further enhance system safety. Additionally, alternative battery chemistries like lithium iron phosphate and solid-state battery offer improved stability and lower safety risks compared to traditional lithium-ion battery.
Energy storage systems in electric vehicles play a crucial role in vehicle performance, efficiency, and safety. To ensure their reliability, several inspection methods are used throughout their life cycle. There are namely 7 methods used in this that I will talk about, which is the visual inspection, electrical testing, thermal inspection, non-destructive testing, NDT, fault diagnosis, BMS diagnostics, as well as the comprehensive approach. Now let's look into what each of these testing methods talk about. First up, visual inspection is the most basic yet essential step, which helps to identify visible damage such as cracks, corrosion, or leaks that compromise safety. Next up, electrical testing ensures the system operates correctly by checking the voltage, current, insulation resistance, as well as the battery capacity. Another key method is the thermal inspection, which uses infrared thermography to detect overheating, poor connections, or cooling system failures. Additionally, NDT, or known as non-destructive testing, uses ultrasonic and X-ray images, which allows for internal inspection without causing any damage. Finally, BMS diagnostic leverages real-time data monitoring to detect faults early, enabling predictive maintenance and reducing unexpected failures. Regular inspection of EV energy storage system is essential to prevent failures. and this helps to ensure user safety as well as extending battery lifespan and minimizing risk. As we know, electrical storage systems are crucial in electric vehicle design. Therefore, to ensure the reliability, various international standards and guide testing and safety procedures are implemented. These are implemented by organizations such as SAE, ISO, UL, as well as IEC. Now, let's look into a few of the international standard procedures that have been implemented by these organizations. First up is ISO 12405, which defines performances and reliability tests for EV battery packs, ensuring they function safely under different conditions. Next up, there is ISO 16750, which focuses on the environmental stresses batteries and electronic components face, such as vibration, temperature, and electrical loads. IEC 62660 sets the testing framework for individual battery cells, ensuring they meet electrical, mechanical, and reliability requirements. UL 2580 ensures safety compliance, covering risks like fire, explosion, and electrical failures in EV batteries. Lastly, SAE J2380 specifically tests battery vibration resistance, simulating real-world driving conditions. All these standards guarantee that EV batteries are efficient, durable, and most importantly, safe for consumers.
Good morning, everyone. So today, for this session, we will be presenting the failure mode and effect analysis (FMEA) for the energy storage system (ESS) in electrical vehicles (EVs). So to ensure a realistic analysis, we make key assumptions, which is the first one: the ESS uses lithium-ion batteries. Second, it operates between negative 20 Celsius to 60 Celsius with regular use from 15 Celsius to 45 Celsius. Third, the system is expected to last 8 to 10 years or 250 kilometers. Fourth, the fast charging with 95% efficiency and a 2 to 3% degradation rate annually. 5. The safety mechanism includes battery management system, contactors, and venting system to prevent failures. 6. The preventive maintenance includes annual sensor calibration and cooling inspection. So now let's look at the FMEA table for the ESS components. First, the battery packs, which is cells and modules. The failure mode is cell overheating with RPN 150. So it will cause a thermal runaway, and to prevent this is to improve cooling and add thermal sensors. So for the battery management system controller, the failure mode is cell malfunction with RPN of 112. The effect is incorrect SOC estimation, and to prevent this, we need to add redundant sensor and regular calibration. Third, which is a battery contactors and safety disconnect. The failure mode is welded contactor with RPN 81, and the effect is prevent safe disconnection during faults. So to prevent this, we need to upgrade the contactors and introduce smart shutdown. And fourth, which is the battery energy control unit (BECU). The failure mode is energy flow imbalance with RPN of 96. The effect is inefficient charging or discharging. So the action to be taken, which is to improve the power balancing and optimize software. Fifth, with high voltage junction box (HVJB), the failure mode is short circuit with RPN of 108. The effect is the pole failure and potential hazard. An action need to be taken, which is to enhance insulation and add safety relays. And six, the battery thermal runaway protection system. The failure mode is failed to detect overheating with RPN of 100. The effect is uncontrolled battery overheating, and to prevent this, we need to add redundant thermal sensors and improve response time. 7, which is the battery venting and pressure relief system. The failure mode is block ventilation with RPN of 96, and the effect pressure build up and explosion risk. And the action needs to be taken, which is to improve the ventilation and decrease filter cleaning frequency. And lastly, which is the energy storage system housing and structural enclosure. And the failure modes is the structural cracks with RPN 84. The effect is it is exposed to environmental hazards, and action needs to be taken, which is to reinforce material and improve structural design. So, in summary, the highest priority failure mode is cell overheating with RPN 150, and we already begin implementing solutions such as cooling system improvement and thermal sensors upgrade.
In conclusion, our FMEA analysis identified key failure risks in EV ESS such as thermal runaway and electrical faults. We propose solutions like enhanced cooling, battery management, and advanced fault detection system to improve reliability and safety. By addressing these risks, we contribute to the development of safer, more efficient energy storage solutions for EVs. Thank you.